Good morning, people. Today we're going to be looking at ring final circuit testing, which is the next part of our testing process. This is a 3-step test, and the purpose of that 3-step test is to check that the circuit is wired as a ring circuit. In other words, it is complete. To check that there's no excessive spurring. In other words, there's you haven't got a spur off of a spur off of a spur, and to ensure that there are no short connections between sockets. Also, in addition to that, when you've completed the full process, the full 3 stages, it will also confirm polarity at each socket. The tester that we require for this is a low resistance ohm meter, and its unit of measurement is the same as continuity, which is the ohm. Most multifunctional testers will have a setting for continuity, but if you've got a continuity tester, it could have multiple settings or multiple ranges within the ohms range. Okay, and you need to select the low resistance or the lowest value. So if we look at a ring circuit, what you should have is a outward leg, if you like, that forms around each socket and comes back on an inward leg. As you can see by the description here, or by the diagram here, there's a break in this the ring circuit here, okay, which indicates that these two 2.5 conductors are no longer in parallel, and there is an interconnection between socket 3 and the last socket. This is quite a dangerous instance, okay, because it'll increase the current that flows down this leg, and of course there will be a inaccurate current flow between these 2 conductors here. So step 1 is known as the end-to-end test, or tests, and step 1 is in effect 3 tests in one step. So here we have our ring circuit. Okay, as you can see, the live conductor goes all the way around for each socket and back to the consumer unit, as does the neutral and the earth. The first stage of our step 1, if you like, is to do continuity of our line conductor, or our little r1. Okay, so we need to connect our meter to our line conductor, our brown one, and it'll measure the resistance around the line conductor, passing through each socket, and then come back on the other inward leg. Okay, and as it shows there, we've got a resistance of 0.3 of an ohm, or 0.03 of an ohm. Okay, so we've verified that that brown conductor, the line conductor, or the little r1, is continuous. As you can imagine, the next step to this is our little rn, and again, as you can see, our neutral should go all the way around the circuit, okay, and then return back to the board. So what we should do when we connect, what we should find when we connect our test meter to our outward leg of the neutral and measure its resistance all the way around the circuit, and then back through our inward leg of the neutral conductor and back to our tester, we should find the value is exactly the same as the line conductor. The reason it's the same value is because our neutral conductor has the same CSA and the same length as our line conductor, therefore should yield exactly the same resistance. A general rule of thumb, 0.05 is the maximum permitted difference between those 2 resistances. Right, the next test we do as part of step 1 is our R2. Okay, and in order to do this, we connect our low resistance ohm meter to the 2 open-ended CPCs, and then record the resistance in ohms, exactly the same way as we did with the previous 2 tests. So we're going to measure the resistance of the CPC, okay, around the earth wire or CPC, and that resistance could be higher than the line and the neutral resistance. Okay, because could potentially have a smaller CSA. The smaller the CSA, the higher the resistance. Okay, so if we've got a 2.5 twin and earth, it'll have a 1.5 CPC, therefore lower CPC value, higher resistance. Of course, if our R2 value or our R2 conductor is the same size, then you will yield the same resistance. So in order to find out what the difference of the resistance would be between a 2.5 and a 1.5, we just put our line conductor in the equation at the top of the line on our division and our CPC beneath it. So our 2.5 would be divided by 1.5, which would yield a difference of 1.66666 reoccurring to 7, okay, or 1.67. So as our CPC has a CSA that's 1.67 times smaller than the line conductor or live conductors, the resistance will 1.67 times higher than those conductors. What would happen if we have a conductor that was a 4mm and a 2.5? Well, exactly the same process. If we put our line conductor in our equation, we would find a 4mm divided by 2.5mm will yield a difference of 1.6. Okay, so if you've got a 4mm and a 2.5, then all you need to do is multiply your line conductor or your live conductors by 1.6, and that will yield the correct results for your R2. Okay. Right, on completion of this video you will need to do task 1, okay, so I'll read it out to you now so you've got an idea. If you have a ring circuit wired in a flat twin and earth and a CPC with conductor size of 1.5 and a 2.5, sorry, a 2.5 and a 1.5, the conductor length end to end is 56 meters. How do you calculate the little r1, little rn and little r2? You can assume the temperature is 20 degrees. You will need an on-site guide or the guidance note 3 to establish the resistance per meter of each conductor. But like I say, do that after you've watched this video. Right, stage 2. So after we do our end-to-end resistance, we do what's known as our polarity, sometimes known as our figure of 8 test, line to neutral. So this time we want to do our interconnections at the board, and we need to test at each socket. So we connect our outgoing line, known as P1 on the board on the diagram here, and we connect using a temporary link between P1, which is our outgoing line, and neutral 2, which is our incoming neutral. We do the same with our incoming line and our outgoing neutral, okay, and then we test at the front of each socket. We could use a plug-in device for this, okay, but it's important to test at each socket, at the front of each socket, so we can verify that the front pins are the correct polarity. Whilst we're there, we can also operate the switches if they're switch sockets, and this will verify that the switch operates the line conductor as well. Okay, we should test at every socket. And we should test at every socket to verify that each result is within 0.05 of each other. You will need to open up the sockets just to carry out a visual inspection, but you must test at the front. Once we've got that result, there's nowhere actually to write that down on the test sheet, but we must record it somewhere. So in a notepad, just verify that you've done each socket, number them 1, 2, 3 in this case, put the resistance of each, and then verify they are within 0.05 of each other. The third and final step of our ring final circuit testing is known as our R1 plus R2, also known as figure of 8 live to earth, and it's very similar as so at the board again we put our interconnections at the board and test at each socket. So at the board we put our interconnection to between P1, which is our outgoing line, and our CPC2, which is our incoming earth, and then our P2, which is wrong on my diagram, we put our P2 to our CPC. Right, I just adjusted that diagram so it makes more sense. So yes, we take our P1, which is our outgoing line conductor, connected to our CPC2, which is our incoming earth, and vice versa. We then again test at each socket, operating the switch, verifying the switch operates just the line conductor. We record this value as our R1 plus R2. Again, each socket should be within 0.05 of each other, and we could expect a different result to our R1 plus Rn, particularly if we've got a lower size CPC and therefore a higher resistance on that CPC. We are able to predict the results by calculation when using our previous test results or equations. So the formula for that is our R1, our big R1 plus our Rn is equal to our little r1 plus our Arn divided by 4. The reason it's divided by 4 is because there's two conductors, but each conductor has a parallel path. Okay, therefore there's 4 parallel paths for the current to go down. Exactly the same formula for our R1 plus R2. Okay, so that'd be our little r1 plus our little r2 divided by 4. Our little r's, if you like, are our end-to-end resistances that we did in step 1 or stage 1. So your task 2, again you can download this clip and also the presentation, so you got the tasks and then complete the task 2 paperwork on Google Class. You need to find the results from task 1, so the little r's, and then calculate the R1 plus R2 and the R1 plus Rm. And the third and final thing is to do task 3. Task 3 is the combination of all of what you've just learnt. Okay, so you're going to do a test for continuity on a ring final circuit. It's to be carried out on a circuit in an office where the loop lengths are 41 metres. So that's 41 metres from end to end of each of the loops. They're connected directly, all the sockets are connected directly into the ring circuit, so there are no spurs. The live conductors are 4 mils and the CPCs are 2.5. You need to explain in detail the 3 stages. Okay, that will enable you to confirm continuity and the polarity of that ring circuit, and also you need to include the test instruments required, how to connect them, and the expected readings at each step. Okay, slightly different, the temperature at time of test will be 25 degrees. Okay, so that will make a slight difference. I've also put the cross-sectional area and the milliohms per metre, and all you've then got to do is provide your answers in Google Classroom. Good luck, and I'll speak to you soon.